All right, so we've got this whole big way of thinking about things, and then I want to apply it to an example. So here's the example that I choose. X prime equals x plus 2y, and y prime equals negative 2x plus alpha y. And I want to leave this alpha sort of unknown or unspecified. It is a constant, so it doesn't depend on time. This is still a constant coefficient situation. But I want to solve the problem without specifying alpha until the end. So that way I can see when I tune the parameter alpha and try different values for it, what will happen. So that will be pretty interesting. So let's write this in kind of vector form, or actually, I'd rather write it like this. X prime is, we've got 1, 2, negative 2, alpha, x. Now, in this situation, I actually would not recommend trying to solve the eigenvalue problem directly, because there are a lot of different things that can happen, right? Like you'll end up with a characteristic polynomial, but your polynomial's coefficients will have this unspecified alpha in it. And actually, no, I take it back. We should start trying to solve the eigenvalue problem, but not go all the way with it, because the alpha is really going to make things complicated. So to figure out where I am in this picture, what kind of situation I'm in of these different possible phase diagrams, I need to first decide, am I on the real branch or the complex branch? Or I could be on this third branch that I'm not talking about very much. I hope not. So let's see, am I on the real branch or the complex branch? The answer could depend on alpha. So let's see. So first question, eigenvalues real or complex? If we answer this, we learn a lot already. Real, then we know it's either saddle node or saddle point or unstable or stable node. Complex, we know it's either spiral or center. Okay, so start solving the eigenvalue problem to answer this. So first, subtract lambda from the diagonal, and then take the determinant and set that equal to 0, and then see what polynomial in lambda that gives you. Let me just work with this object. Okay, that calculation is super boring, so let me just do it here. And I can even be extra lazy and have it collect terms based on what power of lambda they have in front of them. So looks like I got this polynomial in lambda. Let me copy it over. All right, there it is. And the eigenvalues will be the roots of this polynomial, the values of lambda that make it 0. So how can I know what those are? Well, factor the polynomial, or more realistically, use the quadratic formula. So lambda will be negative this thing, so alpha plus 1, plus or minus square root, and then actually what really matters to answer my main question here, are the eigenvalues real or complex, is just what's under the square root. I don't really care about the other stuff. I just want to look at what's under the square root. So it'll be this thing squared, so that's alpha plus 1 squared. Actually, it's negative alpha minus 1 squared, but I'm squaring it, so it doesn't matter if I negate everything. Minus 4 times 1 times alpha plus 4. So my question here, are the eigenvalues real or complex? That's equivalent to the question, is the thing under the square root here positive or negative? That's the question. So is alpha plus 1 squared minus 4 alpha plus 4 greater than 0 or less than 0? Or is it equal to 0? If it's equal to 0, that's the repeated roots case, right? That's where you have repeated roots, and that's the case here that I just don't want to talk about very much. But I will talk about it pretty soon. So let's just focus on greater than 0 versus less than 0. Now, ironically, to find out what values of alpha make this greater than or less than 0, it will be useful to find out when it equals 0. So what I have here is actually a polynomial in alpha. And I want to know when this polynomial in alpha is positive versus when it's negative. Let me continue to be lazy and save myself from inevitably making calculation mistakes. So I'll expand this polynomial. It's alpha squared minus 2 alpha minus 15. And luckily this one, I think, factors nicely. I had that in mind when I came up with the example. I wanted something with nice numbers. So let's see, I think this is minus 5 plus 3. Yeah, so the question is alpha minus 5 times alpha plus 3 positive or negative? And, okay, this is one of these things. I remember learning this in high school, how to do this. For different choices of alpha, is this polynomial positive or negative? Then, well, you know it's 0 when alpha is 5. And you know, and you know when alpha is negative 3, that is also 0. And then in between, you have some positive versus negative behaviors. Well, when alpha is very, very large, when alpha is very, very large, both of these would be positive. Or if you like, the alpha squared would be dominating the polynomial here, and you'd get positive. On the other hand, when alpha is very, very negative, very like negative a billion, then the polynomial here would be also positive, right? Because these would both be negative. But when alpha is between negative 3 and 5, that's when this would be negative, right? Yeah. If alpha is less than 5, then alpha minus 5 is negative, and this would be positive. If alpha is still bigger than negative 3, this would still be positive. So you'd negative times positive, so you'd have negative. And I don't know why I wrote a negative sign here. I think I did say the right thing and I wrote the wrong thing. It's a positive. So what I'm depicting here is along the axis of possible alphas. I'm telling you what is the sign of this polynomial. This polynomial in alpha is what sits under the square root when you try to find out what your lambdas are. And remember, our original question, are the eigenvalues real or complex, is basically the question, is the thing sitting under the square root positive or negative? If it's positive, then we're looking at real eigenvalues. So real lambdas here, real lambdas here. And then if it's negative, so if alpha happens to be between negative 3 and 5, then we're looking at complex eigenvalues. So complex lambdas happen in this range of alpha values. Okay, so actually, for our original differential equation, depending on the value of alpha, whether it's less than negative 3, bigger than 5, or in between, depending on that, you might be on this branch here, one of these possibilities, or on this branch here, one of these possibilities. Okay, well let's look at the determinant and trace to figure out which sub-branches we can possibly be on. So let's start with determinant. What's the determinant of this matrix? So the determinant of 1 to negative 2 alpha is alpha plus 2. Okay, that's interesting. And then the trace of that matrix is the sum down the diagonal is alpha plus 1. All right, and different things happen depending on whether the determinant is positive or negative, and different things can happen depending on whether the trace is positive or negative. So, oh man, there's so much going on in this system. Just by varying alpha, you can get so many different behaviors. I'm giving you things like this on your homework, but I'm not making it. The ones on your homework are set up so that you don't get like all possible behaviors in one system packed in like this. But this one was just fun to do as a lecture example. All right, so let's look at this. Let's think about what. Let's go down to this. Yeah, I think this picture will be helpful. Let's build this picture up. Here's our alpha axis. Let's think about what values of alpha along here are going to lead to what different situations. So we've already sectioned off that you've got real over here, complex in the middle here, and then real over here for the eigenvalues. Now, where's the determinant going to be negative versus where positive? Well, how about I do that calculation off to the side? So determinant is negative. What the hell? Determinant is negative if and only if alpha plus 2 is less than 0. So determinant, let's call it A, negative, if and only if alpha plus 2 is less than 0. So if and only if alpha is less than negative 2. And similarly, the determinant is positive if and only if alpha is greater than negative 2. So let's focus on negative 2 over here. I guess that's here. And over on this side, we have determinant less than 0. And over on this side, everything to the right, we have determinant greater than 0. That is interesting. I think that something here doesn't make sense. Something here is wrong. Yeah, I must be doing something wrong. Because you can't have determinant 0. You can't have a negative determinant in the complex eigenvalues case, but my picture is saying that I do have that. So what did I do wrong? Do you see the problem? Determinant being negative doesn't occur in this here. That if these are your eigenvalues, then the determinant should be alpha squared plus beta squared. That's what we saw earlier. So I think I've done something wrong. Let me investigate. Oops, yeah, I found it. The determinant is alpha plus 4, not alpha plus 2. My bad. Okay, so when alpha is less than negative 4, that's when the determinant is negative. When alpha is greater than negative 4, that's when the determinant is positive. So let me fix this here. All right, that's better. So now negative determinant can only occur in the real region as we expect, considering what we've discussed so far. All right, so that's nice. How about the trace? And I think I computed that correctly, just adding down the diagonal, 1 plus alpha. How about I do the trace in a different color, since things are getting a bit cluttered. So how about I do the trace in red? Okay, so when is the trace, say, negative? So the trace of A is negative if and only if alpha plus 1 is negative. So if and only if alpha is less than negative 1. And similarly, the trace will be positive if and only if alpha is greater than negative 1. So negative 1 is sort of our dividing line there. That'll be somewhere between negative 3 and 5. So over here, trace is negative, and anything to the right, trace is positive. All right, so now let me divide things up again, this time focusing on all the different conditions that are simultaneously holding in any different segment of the line of possible alphas. Okay, you'll see what I mean in a moment. Okay, so here's my drawing. I'm just trying to declutter things a little bit, but this time I want to focus on each one of these individual segments here where different conditions simultaneously hold. And just think about what picture am I in for each of those segments. So like here, what picture am I in here? Well, it's real eigenvalues, negative determinant. That's saddle point. Right? So I'm just using this. I'm going real eigenvalues, negative determinant. It's a saddle point. And we had good reasons for coming up with all of these, right? Like that was because the negative determinant tells us the product with the eigenvalues is negative, so that means the eigenvalues must have opposite sign to each other, and that led to a saddle point in an earlier lecture. Okay, how about in this region between negative 4 and negative 3? Here we have still real eigenvalues, since we're to the left of the negative 3, but now positive determinant. Okay, real eigenvalues, positive determinant, that's here, here. Okay, but is the trace negative or positive? Now I want to know about the trace. I'm to the left of the negative one, so the trace is negative. So real eigenvalues, positive determinant, negative trace, it's a stable node. Neat. And let's see, now from, let's look at -3 to -1. In between here, okay, we've got complex eigenvalues, and then I think the trace is all I need to know about really, because the determinant will always be positive for complex eigenvalues. In this region, the trace is negative, and we've seen that that leads to stable spiral. Solution spiraling in. So that was complex eigenvalues, negative trace, stable spiral. And then in this region, still complex eigenvalues but positive trace, it's unstable spiral. So see all these different pictures that we can get just by tuning this one parameter alpha, by tuning this one little number in the differential equation. Okay, last one. Real eigenvalues now, so greater than 5, real eigenvalues, but now positive trace. So real eigenvalues, also positive determinant, by the way, and positive trace. That's unstable node. So now I care about the fact that it's to the right of the 5, so it's real eigenvalues. It's to the right of the -4, so it's positive determinant, and it's to the right of the -1, so it's positive trace. So here we have unstable node. So look at that, you get so many different things. And here I was looking like strictly in between things, but what happens at some of the different values? Like, what happens if you're actually here? Each of these is like, you could call it a critical value or something like that. I don't know why I'm using green. But like, yeah, like what happens here? That's sort of like a critical value. It's right between these two, that's like a phase transition point. Two qualitatively different behaviors, and this is right smack in the middle of them. What happens here? This is where the determinant equals 0, right? Where the determinant equals 0, that's where you get a singular matrix and you have like a whole line of equilibria. So this is line of equilibria. Right there. And what happens here? That's the transition between real and complex. Huh. That's where this polynomial in alpha vanishes. Similarly, here at 5. That's where what's under the square root, when you're determining an eigenvalue, becomes 0. That's where you have repeated eigenvalues. So that's the, let me just call it sad face case for now, because I just haven't been talking about it. It's this case that I refuse to talk about, but that I will talk about in a moment. And what happens here, this is also kind of neat, between stable spiral and unstable spiral, that's where the trace vanishes. Remember, we saw that the trace, if your eigenvalues are alpha plus minus I beta, your trace is 2 alpha. So when the trace vanishes, that's when alpha vanishes. And so you have a stable center. Now, aren't you just dying to watch an animation of this actually play out in the phase plane? So let me see if I can fit everything here. Yeah, maybe I'll do this. So here it is. So I've set this up to just show a bunch of solutions, and it's going to run alpha from -6 to 6. So this bar manipulates alpha, plays us along this alpha axis. So -6 is like to the left of -4, and then 6 is to the right of 5. So let's see, I'm going to play it as an animation, and this changes kind of quickly because there's so many different behaviors here, right? Okay, so I've slowed down the animation so that it moves kind of, the bar moves kind of slowly. and let's watch it play out. So right now alpha is at -6, so that's the saddle point. And now I'm going to press play, and we'll watch it transition into a line of equilibria and then to stable node behavior. So this is our saddle point, right? They look kind of like these. They look like this. These red curves here are what we're seeing, these like curvy solutions. Okay, so here goes. So watch it slowly changing as alpha increases. You can see the value of alpha here. And it's about to hit -4, and it just passed by. But you saw it kind of became this line of equilibria picture, right? Let's try it exactly at -4. The trajectories are like linear trajectories, and there's this line of equilibria that's not being depicted here, but it's there, and everyone's going towards the line of equilibria. Why do I say towards? Because the trace is negative over here. Okay, so then let me continue playing it. Now we're in stable node region. So this picture unfortunately doesn't show you the arrows on the solutions, but if they were there, they would all be pointing in. So these solutions are all coming in, and they decay towards 0. Okay, we're now at -3.1. It's about to hit -3 and transition into a spiral. Now, we passed by the sad face along there. Okay, I'll come back to the sad face in a moment. So this is a stable spiral. Again, there are no arrows, but if there were, they would be pointing in. These solutions are spiraling in. Then we're about to hit stable center, so that's at -1, playing again. There it is. We're very close to it. That's a stable center. So right now it's not exactly -1, it's a little bit less, so it's still stable spirals. But since in my parametric plot I only let t run over a finite range, because I have to, for it to know when to stop plotting things, you see sort of this artificial endpoint here where it stops. But if you let time continue running, it'll just spiral in very, very slowly. Okay, and now we're about to transition past stable center. Now we're in the unstable spiral region, so the arrows will be pointing out. And let's watch it play all the way up to 5. After 5, it'll become an unstable node. So still unstable spiral right now. And we're about to hit 5. And there it is. Now it's an unstable node. You didn't really see anything suddenly change, right? Okay, and it restarted. So you didn't really see anything suddenly change between 5 and 4, right? But interestingly, if I type in 5 for alpha, like exactly 5, then I get a bunch of errors and it poops out. That's because I never wrote in how to actually deal with those cases. So if you're interested in seeing how to write solutions for these specific cases here, then check out section 443 in your textbook. But I'm not going to ask you guys to read that, just because it's honestly not that interesting. What's more interesting to me is just watching this play out and watching it transition over those points. So let's look at that transition again across -3. Where to the left we had stable node, and then to the right we have stable spiral. These are called degenerate nodes, by the way. So see this transition? Stable node, and then it becomes a stable spiral. So what is really going on like at -3? Well, over in this region, you have like 2 eigenvectors, right? And I don't know exactly which way they point, but you've got 2 eigenvectors, and solutions are sort of coming in along the eigenvectors. So there's these 2, let me draw the lines along which the eigenvectors go. You've got these 2 eigenvectors, solutions are coming in like this. So maybe your solutions look something like this. And then what happens is you tweak alpha and send it that way. Then actually what's going on is you find these eigenvectors get tighter and tighter. They sort of close like a pair of scissors. And then when you get to this point, you have just one eigenvector. That's when it's fully closed. That's a situation where you have repeated eigenvalues, but not enough eigenvectors. You only find one eigenvector while you have, for that one eigenvalue. And if you continue to increasing alpha past here, then there are no eigenvalues, or rather the eigenvalues are complex. So your eigenvector disappears. There are no eigenvectors. So it's sort of like a pair of scissors that closes gradually, and then it's fully closed when you reach -3. There's only one eigenvector. That's the degenerate node. And then if you pass -3, then this vanishes. Even this vanishes, and you have stable spirals. So at this moment, you have something like this picture, but also looking sort of like a spiral. Something, let's say the origin is here, something like this. And that's a degenerate node. If you continue and then increase alpha past -3, then you'll start getting actual spirals. Okay, so this is really fun to play with. Hopefully, so again, for the ones you have on your homework, you're not going to get all of these different behaviors all packed into one line of alphas, but you'll get a few of them. And hopefully you can see how this might be very useful. In real life, you don't have actual differential equation systems. I mean, in practice, not in real life, but in practice when you're doing mathematical modeling, usually you don't have like fixed differential equation systems. You have them with parameters. You look at families of things, right? And you can see how much richness we got, how rich of a variety of behaviors we got just from having this one parameter sitting there. So in the next lecture, we'll look at some application type problems where you've got parameters, and it's a lot of fun.